Welcome back. We are going to look at a problem involving a vapor compression refrigeration cycle or a VCRS cycle. This says it is working with refrigerant R134A and the evaporator and condenser temperatures are given as -5 degrees and 30 degrees respectively. We are asked to find out the compression work, refrigeration effect, heat rejected, COP and cycle efficiency. So, we will go on to all of these, but first let us draw the cycle on say a TS diagram. So, we have this happening in the liquid vapor dome. Ideally, we would start compression at the vapor saturated vapor condition. We would compress to some condition. We would have a constant pressure heat rejection. We can call this as sum 2. We would have an isenthalpic highly irreversible expansion in a capillary tube, and then we have constant temperature and constant pressure heat addition in the evaporator. So, this is our compressor, this is the heat exchanger or the condenser, 3 to 4 is a capillary tube or an expansional valve, and 4 to 1 is the evaporator, which is cooling the stuff which we want to have. So, we need to find out the compression work. Okay. So, the compression work from the first law for a flow process, assuming steady state, assuming there is no heat transfer, the compression work essentially comes out to be enthalpy at the inlet minus enthalpy at the outlet. So, this enthalpy at the inlet is smaller than the enthalpy at the outlet, this work will be negative. The refrigeration effect is essentially amount of heat we can remove over here. From the first law, that comes out to be enthalpy at the exit minus enthalpy at the inlet. The exit is 1.1, inlet is 0.4. So, this is refrigeration effect. Heat rejected in the condenser, we are typically calling it as QH. Heat rejected in the condenser is what we are rejecting in 2 to 3. Again, from the first law, assuming steady state and assuming changes in potential and kinetic energy are small, that is also an assumption we have made in these two cases. So, assuming those, the heat transfer comes out to be enthalpy at the exit, which is H3, minus enthalpy at the inlet, which is H2. COP is what we want, which is the refrigeration effect, QL, divided by what we need to give, which is W, all positive quantities here. QL is anyway positive because it is heat going into the system. W would be negative, but when we are defining COP, we are always defining it as positive values. So, if you want to be very particular about how we write it, we can write as mod of W. This is W in the compressor. The cycle efficiency is essentially defined as the efficiency of this cycle compared to the efficiency of a Carnot cycle operating between the same temperatures. Or in this case, sorry, we are looking at a refrigerator. So, it will be defined as the COP of this cycle divided by the COP of so, the cycle efficiency is defined as the COP of this cycle divided by the COP of a Carnot cycle operating between the same two temperatures. So, the Carnot cycle would be the most efficient cycle to use for as a refrigerator between these temperatures. We are actually using a VCRS cycle, which is different from the Carnot cycle. This has losses. So, for example, we are doing superheating here. This leads to some losses because we are not doing constant temperature heat rejection. Similarly, we are not doing isentropic expansion, we are doing isenthalpic expansion, which is irreversible. So, that leads to some losses. So, the COP which we get from this cycle will be different from the COP of a Carnot cycle, and the ratio of those is essentially what we call as the cycle efficiency. So, these are the things which we want to find out. This is again in the two-phase region. So, we need to refer to tables. We have looked at these kind of tables for steam and water mixtures earlier. We will now look at the table for R134A, which is a refrigerant. So, we will look at tables of these. So, I have over here, for example, two sets of tables for this. So, I am looking for data between minus 30 degrees, minus 5 degrees centigrade and 30 degrees centigrade. So, that is what I want. So, I have here a table from a textbook for R134A. So, it says a lot of things, but the important thing is that R134A stands for 1112 tetrafluoroethane. It is a hydrofluorocarbon. So, it has it's essentially a derivative of ethane, which would be 2 carbon atoms with 6 hydrogen atoms, but some of these hydrogen atoms are replaced by fluorine. So, which then gives us this substance. So, what we are interested in at the moment is to find out the values between minus 5 degrees and 30 degrees centigrade. So, these tables are to be read in the same fashion as our steam tables. It has temperatures, it has pressures, it has specific volumes of liquid and vapor. In this particular table, what we see is the specific volume is for the liquid has been multiplied by 10 power 3. So, which means that if I am looking at this value 0.8421, I should, when I am taking the value, I should take it as 0.8421 into 10 power minus 3, because it's after multiplying by 10 power 3, I get these values here. It has specific volume of vapors. It has specific internal energy UF, which is for the liquid, UG, which is for the vapor. It has enthalpy of liquid and vapor, entropy of liquid and vapor. What we see over here is for the entropy, the reference is taken as minus 40 degrees centigrade. So, it says the entropy is 0 at minus 40 degrees centigrade. So, as long as we are looking at differences in entropy, it does not matter what the reference is, but what we should be careful about is, for example, to take entropy or even enthalpy for that matter. Enthalpy also is taken as 0 as minus 40 degrees centigrade. So, if I take a value, for example, at minus 5 from this table and take a value for say some other temperature from some other table. So, I have another table over here. So, this is also properties of the same substance. So, if I take for example, the value for some other temperature from some other table, for example, minus 40 over here, if I take the value from this table, what I would see is that they do not match. So, I should not do that, because this particular table over here has the reference temperature with 0 value of enthalpy as some other temperature, as some temperature lower than this, whereas the other table has the reference as something else. So, if I was to look at, for example, this table over here, it would tell me somewhere that the reference is something else. So, the critical pressure and temperature are given here, which is 101.08 degrees centigrade and 4000 kilopascal. So, that should be the same in both the tables, but the reference from which the values are taken are different. So, here the reference point is taken as 2000 kilojoule per kg at 0 degrees centigrade and 1 kilojoule per kg Kelvin for entropy at 0 degrees centigrade, which are different from those in the other table. So, you can use any of these tables. The differences should be typically consistent, but if you take one value from one table and another from another table, that is not going to be consistent, but that is also true in the case of steam. So, that is something we should keep in mind. So, for the purpose of this problem, what I need is enthalpy at 1, at 2, at 3 and at 4. So, let me start with 1. Point 1 refers to the evaporator. So, the evaporator temperature is minus 5 degrees centigrade. The condenser temperature, which is essentially this part of the temperature, refers to 30 degrees centigrade. So, what I need now is the evaporator enthalpy, which is saturated vapor at minus 5 degrees centigrade. So, let me look at this table. For saturated vapor, which is this at minus 5 degrees, the value is 247.55 kilojoule per kg. I need the enthalpy at 2. What I know at 2 is that the pressure is the same at 3 and at 2. So, what I can see is what is the saturation pressure at point 3. So, the saturation pressure at 30 degrees centigrade I need to find out from the table. So, at 30 degrees centigrade saturation pressure is 770.6 kilopascal. So, P2 equal to P3 . So, how do I find point 2? Point 2 is the intersection of this constant pressure line going from 3 to 2 and the constant entropy line going from 1 to 2. So, what I need is, I know that this is in the superheated region, it is on the right of this dome. I need to find out at this pressure in the superheated tables a value which has the same entropy as point 1. So, let me find out the entropy at 1. So, entropy at 1 is vapor entropy at minus 5 degrees centigrade. So, at minus 5 degrees centigrade, vapor entropy is 0.9345 kilojoule per kg Kelvin. So, now I am going to look at this superheated tables, look at this pressure and this entropy. So, pressure at 770.6 kilopascal and entropy of 0.9345. So, first superheated tables. So, here the pressures are listed. I want 770 kilopascal. So, I can interpolate between these two, between 700 and 800. So, (770) minus 700 by 800 minus 700 should be what I am looking for is actually entropy values. So, I am actually looking for, I need to find a point on this. So, the temperature values which are given here, this table is not sufficiently, it does not have sufficient gradations which it can do. So, what I am going to do for the as a first cut approximation is, let me assume that 770 kilopascal is close to 800. So, if I assume it as close to 800, what I want is to find out a temperature. These are temperature values here. I want to find out a temperature at which the entropy value I had earlier is listed here somewhere. So, if I was to, so the entropy value we had is 0.9345 kilojoule per kg Kelvin. So, if I was to take it as 800 kilopascal, what I see is this value is lower than this. So, this is not a useful table for me. So, if I had actually the values listed at say 750 or 760 or 770 kilopascals, I would be able to find it. So, let me assume for the moment that the pressure I have is equal to 700. So, if the pressure was 700, what I see is that the temperature, that the entropy lies between this value and this value, which means the temperature lies between this value and this value. So, the entropy which I have is somewhere between these two, which means my point lies between these two temperatures. which means my enthalpy will also lie between these two values. So, what I am going to do is to take these two values and assume that the pressure is close to this and take the average of these two values and take that as the enthalpy which I have. So, the reason we are doing this for this particular problem is that we do not have the value directly listed on this table. But what I can also do, since at this moment I have access to another table which is more detailed, is to see whether the values are listed here in this other table. So, what I am looking for is actually 770 kilopascals. I have a value here for table with 750 kilopascals, which is fairly close. But if I am going to take one value from here, I need to take all the values from this table, because as I said earlier, the references are different. So, what I need to do in this case is to go back and find out new values of these using these new tables. So, this is going to be the same, but the enthalpy. So, enthalpy at 1 is minus 5 degrees centigrade and saturated vapor. So, what I want is saturated vapor minus 5 degrees centigrade. I want Hg, which is 395.9. I also want entropy of the vapor, which is 1.7308. The pressure is 243.39 kilopascal. At minus 5 degrees and saturated condition. But we are not looking for pressure at 1, that is pressure at 1. What we want is pressure at 2. So, 2 is at 30 degrees. So, the pressure is 771 kilopascal, which is the same as in the other tables. I was a little surprised that we are getting a different pressure value, but we were just looking at the wrong point. So, what we want now is something close to 770, because that is the pressure in this line, and we want an entropy close to this. So, let us go to the superheated tables and find a value close to 770. This is 110, 150, we have 725, we have 750, and then we have 800. So, let us take 750, it's fairly close. And in this, what we want is an entropy value. Entropies are given here of 1.7308. 1.73 is somewhere here. So, this is close enough. So, if I am taking this, it means that my temperature is 35 degrees centigrade and the enthalpy is 420.8. So, what we see is T2 is approximately equal to 35 degrees centigrade. Enthalpy at 2 is approximately equal to 420.8. Point 3 is liquid at 30 degrees centigrade. So, I can find out its value from the saturation table. 30 degrees, and I need HF, which is 241.8. Three to 4 is a throttling process. We discussed that during the throttling process enthalpy remains constant. So, H4 is equal to H3. So, now we have all of the enthalpy values. So, we can just substitute it here. Is H1 minus H2 which is minus 24.9 kilojoule per kg. The value is negative because it is work done on the system, or if I want mod of this, I can write it as positive. QL is H1 minus H4 This is 154.1 kilojoule per kg. This is H3 minus H2. Is minus 179. It is negative because it is heat going out of the system. If I want the positive value, I can just find out mod of QH. COP comes out about 6.1 or 6.2, and this is essentially 6.2 divided by COP of the Carnot cycle. The COP of the Carnot cycle would be whatever is the heat transferred divided by the work done. So, it would be something like this. We can also write this as QL divided by so if I multiply this and divide by QL, so I have this QL which goes, and I have QH by QL minus 1. So, this is 1 by QH by QL minus 1, and for a Carnot cycle, because it is reversible, ratios of heat can be given as ratios of temperature. So, I get 1 by TH by TL minus 1, or this is essentially TL by TH minus TL. So, it comes out to be similar to this, but the way we get it is like this. So, the heat transferred is not proportional to the temperature, but the ratios of heat transfers are proportional to the ratios of the temperatures. That is what we see, and our temperatures here are minus 5 degrees centigrade and 30 degrees centigrade, but when you are using this formula, it is only valid when temperatures are in Kelvin, and here it is 273 plus 30 minus of 273 minus 5. So, essentially we have 268 divided by 35, which is 7.6. So, going back here, this is divided by 7.65, which gives a value of about 0.8, is 80%. So, what we see is that this VCRS cycle which we have theoretically is about 80% as efficient as the Carnot cycle would be if we ran it as a refrigerator. So, what we see is that the Carnot cycle itself gives us some COP which is less than infinity, and the VCRS cycle says that you can't even reach that. So, Carnot says you can't get an infinite COP, you have to do some work in order to transfer heat, but because we are not able to, and that is the maximum we can possibly have. But the VCRS cycle, because of the way in which the cycle is constructed, says we first of all have a limit of Carnot, but we can't even reach the Carnot, we only get lower than that, we can only get about 80% of what we could have got with the Carnot cycle, and this is a theoretical maximum. And if we really run a system using this, we would have losses in 1 to 2. We could have, for example, in the real case, we could have a non-isentropic compression. We know how to deal with this. Isentropic efficiency would be given, and we can find out the real change in enthalpy, which means we will do more work. So, the real COP in that case would come down even lower than this, plus we can have losses in the condenser and evaporator because of pressure drops, and we can have heat transferred out and so on. So, because of which we would have even lower COPs than this. But this generally tells us how to deal with the problem on this VCRS cycle.